Hello, welcome to our notes about torque. Just as kinematics is the foundation of linear, the study of linear mechanics when we're talking about forces and momentum and energy and even circular motion, you really have to understand kinematics to understand those. Torque is kind of the foundation of rotational motion. You need to understand torque before you can go and understand things like rotational dynamics or objects that roll or objects, anything that has an angular momentum. So that's why we're starting with torque. When I was in high school and I learned this for the first time, this was a fairly, for whatever reason in high school, I felt this was fairly difficult. When I learned it in college the next year, I said, I don't know why I had so much trouble with this. This is actually a fairly straightforward concept. The definition of torque is a twisting or rotating of an object as a result of a force acting on it. A twisting or rotating of an object as a result of a force acting upon it. Okay? Now, sometimes this makes people think of circular motion. That is not the case here, okay? We are not talking about circular motion where an object is just like in orbit around another object. We are talking about an object that is literally rotating. It's changing its orientation. Okay, it's changing its orientation with respect to some other position. Now, that kind of makes it sound like a torque is like a force, and they are similar, but they are different things. What factors affect how much an object twists or turns? I'm going to draw you a picture here, and I wish I could, in class I will definitely demonstrate this for you. I'm going to just draw a picture of a door. Okay, here's your standard door. You can imagine this is any door that you've ever seen before. We're going to say that the hinges of the door are over here on the left-hand side. And if the hinges are on the left-hand side, and if there's a doorknob on this door, where would it be located? Okay? Think about it. It's not located just anywhere on the door. It's probably located over on the right-hand side. There's a reason for that. Okay? You can try this with any door. I could try this with my classroom door. I could try this with doors in my house or my apartment or wherever. You can do the same thing. Let's say that you want to open the door or you want to shut the door, whatever the case may be. What factors affect how easy it is for you to open that door, to twist, in other words, the door, to change its orientation with respect to, I guess, the door frame, okay, or to turn that object? Well, obviously, one of them is going to be how strong the force is. In other words, the magnitude. Anyone who's ever slammed a door knows this. You can get a door to shut very rapidly. It's very easy to shut a door if you push it with a lot of force or pull it open with a lot of force. You can very easily do that. Okay, so the size of the force matters. But let's talk a little bit about the placement of the door handle. Imagine if a door handle was located in the middle of the door. Or actually, better yet, try opening or closing a door by pushing on the middle of the door. Not where the door handle is, but by pushing on the middle of the door. You will see that it's not as easy. Then try and do the same thing by pushing near the hinges. You will find that it's almost impossible to get that door to move. However, if you push or pull near where the handle is, you'll see that it's really easy to open or shut the door. It's very easy to cause it to rotate. So that's kind of interesting. It seems that the ease of causing something to twist or turn not only has to do with how strong the force is, but it also has to do with where the force acts in relation to, well, in this door's case, it's the hinges. We would call that a pivot point, or even better, we would call it an axis of rotation. This dotted line that I'm going to draw in is the axis upon which the door rotates. So axis of rotation is the word that we're going to end up using a lot, or the phrase we're going to end up using a lot in this particular topic. And we abbreviate that sometimes to save some time by AOR. Okay? So not only does the ease of twisting and turning depend on the strength of the force, it also depends on where the force acts. And there's one other factor. There's one other factor that increases or decreases the ease of opening or shutting the door. Now, we already said that a strong force will cause easy turning or twisting. It seems to be that the farther away from the axis of rotation the force acts, the easier it is to cause twisting or turning. Imagine you had a force on the door, but instead of, pushing the handle, kind of into the page or pulling the handle out of the page, imagine that you pushed on the handle in this direction. You're applying a force, it's really far away from the axis of rotation, but if you push this handle, let's say, from the right side, so to the left, you're not going to open the door, okay? That's not going to do anything. If you try to push the handle in, I guess, kind of at this angle, you will get some effect, but not nearly as much as if you push the handle, in this case, straight into the page or pull it straight out of the page. So it also seems to matter the angle at which the force acts. The angle at which the force acts also seems to matter in terms of calculating how big this force is going to be. We're going to take all of these and we're going to write an equation so that we can calculate an individual torque, the torque from a force. Now, if you have multiple forces, they could create multiple torques on an object. We'll talk about that down here. Okay, how can we calculate an individual torque? The equation for torque, well, the symbol for torque, first of all, is this funny looking T. It almost looks like a pie with only one leg. It's not T, don't call it T. It is the Greek letter tau. It's a capital tau. And it stands for torque. Okay, so call it a tau or call it torque. Don't call it T. The equation for calculating torque is R times F times sine of theta. Now, let's go over what these are. F is very straightforward. F is simply the magnitude of the force. I'll write that in a second. R is a little bit more of a tricky definition. R is the displacement, in other words, a length vector from the axis of rotation to where the force is applied. In other words, imagine drawing a vector from where the axis of rotation is straight out to where the force is being applied. That is the definition of R. It is a vector. By the way, if object is in what we would call rotational equilibrium, you get to choose where the axis of rotation is. Okay? If something's in rotational, well, first of all, equilibrium means that when we learned about equilibrium in terms of forces, it meant that the forces were balanced. There was no net force. Rotational equilibrium, the other one's really called translational equilibrium. Rotational equilibrium means that the forces are, or not the forces are balanced, but the torques are balanced. In other words, there is no net torque on a system. And again, we'll talk about net torque a little bit later. So if an object is in rotational equilibrium, you get to choose where the axis of rotation is, because what should be happening is the object is not rotating, or at the very least it's rotating at a constant rate. You can choose where the axis of rotation is. Again, that will make much more sense once we get into some examples, but I did have to say it here. F is simply the magnitude of the force that is acting to try to cause twisting or turning. And theta here, you have to be a little careful with theta. Theta is not going to be measured in radians. Almost a lot of stuff is going to be measured in radians in this unit. Theta is not. Theta is also not necessarily the angle that is going to be given to you in a problem. Theta is the angle between R and F if they were drawn tail to tail, meaning originating from the same point. That's a key here, okay? If you're trying to figure out what the angle between R and F is, draw them originating from the same point. You might have to move like if you were drawing an actual picture of what's going on, you might have to move one or the other, but draw them as if they're originating from the same point, and you will see what that angle should be. Okay, angle between R and F if drawn tail to tail. It's very similar to in the work equation, work equals force times displacement times cosine of theta, where theta was not necessarily the angle of a ramp or whatever else was given in the problem. It's the angle between F and D. Okay? Now, one last note with the theta, and again, this will make much more sense in a few videos when I talk about this method. If the angle is not very obviously 90 degrees, then I highly recommend that you use what we call the line of action method. And again, in a few videos, I will explain exactly what the line of action method is. Okay, so the equation itself is pretty simple. Torque equals R, the displacement from axis of rotation to where the force acts, times the size of the force, times the angle, times the sine of the angle between R and F. The units, as you might be able to deduce, units of R, the displacement, are meters. Units of force are newtons. And sine of theta, well, theta is measured in degrees, but sine of theta just gives you a number. So the units are meters times newtons, or what we really refer to them as Newton meters, N times M. One note of caution, they are not equal to joules. Now, technically, you could write a joule as a Newton times a meter. However, and this, I don't remember exactly why this is the case. This is a Newton meter. A joule is also technically a Newton meter, but torque is not ever measured in joules. Do not tell me that the units of torque are joules. They are very specifically Newton meters. There's a reason for it. I can't quite remember what it is off the top of my head, but do not say that the units of torque are joules. They are Newton meters. Okay? And then one last convention thing to clean up before we get into the rest of this. If a torque causes an object to rotate clockwise, by convention, it is negative. Convention means that's what we usually do. Just like up and right are by convention usually positive. Doesn't mean they're always going to be positive. It's up to you, but most of the time they are. If a torque causes an object to rotate in a clockwise fashion, it is usually considered to be negative. If counterclockwise, if it causes a counterclockwise rotation, then it's usually considered to be positive. Okay, think about a little axis right here. Okay, we measure around this way. This is counterclockwise. We usually say that these are positive angles. They're also going to be positive torques. Okay, there's a little bit about how to calculate an individual torque. Let's take a step back for a sec and see what torque corresponds to for linear motion. We already kind of talked about this, but we're going to keep doing this. We're going to keep making this chart just to show you that these variables that we are coming up with now in this rotational motion unit are essentially the same things we've been talking about all year, but instead of talking about rectilinear motion, we're now talking about angular motion. So for example, in linear motion, D stands for displacement or distance. It measures how far something has traveled. In angular motion, we don't care about how far something has traveled. We care about how far something has rotated, how much of an angle it's rotated through, or the angular displacement. And the symbol for that is theta. Likewise, we care about the linear speed of an object, how fast it is moving from point to point. When we're talking about rotational motion, we don't care about point-to-point speed. We care about the rate at which the angle, or the rate at which something is rotating, the rate at which its angular displacement is changing. Linear acceleration, the rate at which the linear velocity changes is a. Angular acceleration, the rate at which the angular velocity changes is alpha. And the new one in order to cause an acceleration, in order to figure out how big of an acceleration an object has, we do a sum of the forces. We find the net force on an object. In angular or rotational motion, in order to find the angular acceleration of an object, how the angular velocity is changing over time, the rate at which it changes over time, we don't find a net force, we find the net torque. So torque is not the same thing as force. It is the rotational analog, meaning there's some similarities. It acts in a similar way, but they are not the same thing. Force is not torque. Forces and torques are not exactly the same, but they are similar. While an object's linear acceleration depends only on the magnitude of the force, so force magnitudes and directions, but the angular acceleration, the rate at which the angular velocity changes over time, that depends on these things, plus where the force is applied. Okay. Linear acceleration depends on the size of the force and the direction. Angular acceleration depends on those things and where the force is applied. So torque, not quite the same thing as force, but related. Now, what happens when there are multiple torques on an object? Well, back when we learned about forces, if there were multiple forces on an object, that meant that you had to find the net force. And the net force was equal to F1 plus or minus F2 plus or minus F3 plus or minus etc., 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 however many forces there were, and that ended up being equal to m times a. When we were talking about rotational motion, not just translational or linear motion, we don't necessarily care just about forces, we care about the torques. So what happens if there are multiple torques on an object? Well, very similarly, you need to find the net torque. The net torque is simply the sum of the torques in a certain direction. So torque 1 plus or minus torque 2 plus or minus torque 3 plus or minus etc., etc., etc. And that is not going to be equal to m times a. It is equal to something else this time. It is equal to I times alpha. Now you know what alpha is. Alpha is the angular acceleration, but I needs a little bit of explanation. I is what we would call the rotational counterpart to mass. It is known as the rotational or inertia. I prefer the term moment of inertia. The moment of inertia. Okay, but you might also hear rotational inertia. The definition of rotational inertia, or moment of inertia, is how hard it is to rotate something. Okay, how hard it is to make something rotate. And it is based on the shape of the object, the mass of the object, and the axis of rotation. And I'll do a quick little demonstration here. We'll see if it works. It may not. I will go over this more in class as well. I have my water bottle here, okay? Now, it is very easy for me, it's very simple for me to rotate this water bottle like this, okay? You can see I'm just kind of spinning it like so. In this case, the water bottle is rotating about an axis that is along the length of the water bottle. It's very easy to rotate it like this because the mass contained in the water bottle, both the bottle itself and the water inside, are very close to the axis of rotation. Now imagine if I wanted to rotate the water bottle about an axis right here. That would mean flipping the water bottle over like this. Now, the thing is, it's not much harder to do this, but it requires much more effort on my part, especially if, let's say, I want to rotate it like this. I actually have to work a little bit at this. This is actually like tiring my arm out, whereas I could sit here and do this forever, okay? So it actually changes how easy it is for me to rotate the water bottle based on where the axis of rotation is. It would also be a little bit different if I were to decrease the mass of the water bottle, obviously. But what I'm really focusing on here is the moment of inertia is simply how hard it is to rotate something. It was very easy to rotate when the mass was close to the axis of rotation. If I try and rotate it and I have an axis like here, meaning the water ball just kind of like flips around my finger like this, think about how far away some of that mass is from the axis. Some of it is all the way up here. Meanwhile, if I rotate it like this, the farthest away any of the mass is just the radius of the water bottle away, much closer. So this is actually much harder to do than this. Therefore, the moment of inertia for the water bottle rotating like this is much lower than the moment of inertia for a water bottle rotating like that. And the higher the moment of inertia, the lower the angular acceleration will be. Okay, the higher the moment of inertia, the lower the angular acceleration will be. Just like the higher the mass, the lower the linear acceleration will be. We'll talk a lot more about moments of inertia, and you'll develop some intuition for it as well, but that's the definition that we're going to go with for right now. It's how hard it is to rotate something. It is based on the object's mass. Typically, more mass means higher moment of inertia. The shape, if it's a shape where some of the mass is very, kind of at weird locations or very far from the center of mass or the axis of rotation, that increases the moments of inertia. And just where the axis of rotation is in the first place. You can have the same object have different moments of inertia if there are different for different axes of rotation. That's enough about that for right now. Let's finish up just by talking about what we do in order to find the net torque. Obviously, we need to figure out all these individual torques. We need to figure out what forces are causing torques on the system. So to determine what torques are acting, we simply draw a free body diagram, but it's not just the free body diagram you've been doing so far this year. You were drawing a free body diagram. You used to reduce the object down to a little dot. Now you are drawing the free body diagram for the entire object. You need to draw the actual shape for torque, okay, and all the other rotation stuff we're going to do. For the entire object, not just a dot, and show exactly where different forces are acting. And the reason we do this is so that we can get a sense of where the forces are acting, so we can measure those displacements to calculate R. So we do this to be able to measure displacements R. In the next video, we're going to do some notes on this. We're actually going, or not some notes, we're going to do some examples so you can get a feel for how this is actually calculated and used. I'll see you then.